Welcome to practice on the items you need for the first practice test. So, one of the questions, the first one in fact, says find the rate of change of the function defined as the square root of x on the interval 2, 6. And the things to remember from algebra, that these are square-sided brackets. Therefore, we know 2 and 6 are going to be included, and therefore the endpoint of the interval. We're going to use the formula f of b minus f of a over b minus a, which means plug in these endpoints in this function and see how things change. So we evaluate the function at the end, take away the value of the function at the beginning, and divide it by the ending input minus the beginning input. I think of it as rate of change over interval. You always measure where things ended compared to where they started. Think of weight gain over the holidays. You take your weight in October 30th and your weight again on January 2nd. So you're going to take your ending weight, subtract your beginning weight, see how much you gained, and divide it by the time that had elapsed. Then you know your average weight gain per day during the holidays. For our function, it's square root of 6, the endpoint, minus the square root of 2, the beginning point, over the change in interval of input. So these have to match down here, 6 minus 2. So it's input and the function acting on the input to give us output. My calculator told me that that's 1.035 over 4, or about 0.26, which means a pretty soft slope, about a quarter rise up for every unit of run. And we have no other context to put in, dollars, cents, time, money, anything, so we'll leave it like that. Some rules of logarithms and exponents that y'all just need to know, and then once you know them, you won't have to memorize them because you'll be using them. The first one says we have two things multiplying each other, both of which are raised to a power. So that means each one feels the effect of that power, and they're still multiplying each other. This one, we see them multiplying each other, and they have different powers. So we can't write it parenthetically like the first one, but we can show that we can use the common base and add the exponents up there. It's like 10 squared times 10 cubed is the same thing as 10 to the 5th. You can simplify and add the exponents. This one is a power raised to a power. So our 10 squared, like 10 raised to the 3rd power, or cubed, is the same thing as 10 to the 6th. So we're going to show that when this happens, we multiply the power on the base times the power it's raised to. Here we have log of a product. So the best way to handle this is to write log of x plus log of y. Think of it as log of 100, where 100 is multiplied by 10. So we could add the log of 100, which is 2, the log of 10, which is 1, and get 3, which is the same thing as 100 times 10, asking for its log, which would be 3. And again, you could check that with multiplying this, getting 10 times 100 or 1,000. Log of 1,000 is 3. And when you see log, unless you're in Wolfram Alpha, which is a wonderful computer program, it means common log or base 10. Wolfram, for some reason, uses this to represent natural. When I write it, I'm going to write LOG meaning common log, base 10. We spend most of our time in natural logs, but we've got to learn some rules and various basics. So let's look at the other column. Can't do a thing with this. These are numbers in and of themselves, so this is itself, log of A divided by log of B. You probably saw that in the problem on Pakistan's population. You had divide one log by another. This one is probably the handiest rule in all of the work we do with logs and exponents. This is a base raised to a power, but logs bring things down to mainline action, and they bring exponents down so we can work on them and solve for them. So by virtue of taking its log, we're bringing this n in front and using it as a multiplier. Logs are exponents, and it's saying this is an exponent, and we're going to bring it down and use it as such in the realm of mainline action. So it's going to be n log x. This is itself. The ln refers to natural logs or base e, and it says, excuse me, what power do I put on base e to turn it into e to the x? Well, it better be x, because that's what you want to turn it into. And this one says, I'm in base 10. This one also referring to base 10 log. A little bit of 10 there, not ever written. Says, I want to put some power on 10 to turn it into x. Don't know what that power is, not going to solve for it, but when I find it, or what this expression is worth, I'm going to use that on 10, and voila, it's going to turn 10 into x. So these are the basic ones you'll be using a lot. Of course, there are some others you might consider just as basic, but knowing these will get you off to a very good start. There are two questions on the board this time. The first one deals with the population of Matistan, which is given in millions, and the question is, how do we read these expressions? M of 9 and the derivative of m evaluated at 9. Totally different things. The first one is the function itself, so input being years, 9 years after 2000. So in 2009, the population of Matistan is 20 million people. Just evaluating a function and reading the answer. This one is the derivative. How much is the function changing in 2009? And I would tell you the limit is instantaneous rate of change. You have to work with the units you're given. So the rate of change here is going to be people per year, because the output of the function is people, and the input is time. So we're watching the population change with time. The given number is 0.12, and so we're dealing with millions, and if you want to convert 0.12 times 10 to the 6 or a million, it comes out to 120,000 people per year. And again, the people per year is real important to learn about derivatives, the output changing per unit time. And it's usually time, sometimes something else, or investment, dollar, whatever, but it's always a rate of change. When you see the derivative marking like that, you know we're going to talk about output versus input, particularly a unit of input, time, a dollar, whatever. So be careful that you always have 2 units in your answer. One in the numerator, one in the denominator. So I squeezed the graph on this board as well. Interesting little graph. And there are some empty circles, meaning the function couldn't be defined there. It was defined there. It was defined here, and then there's a gap in the function, so not a continuous function. Something else you're learning in this chapter. So definitely a discontinuous function with holes and breaks and holes in it. Excuse me. Okay. So we're following this interesting little function along. When we see a black dot, we know that's what the function is defined as. These are the things it would like to be. It's heading that way. It's sort of like seeing a pothole in a road. You want to go there, you know there's a pothole, but you know where you want to go. And limits are where you want to go. So when you see a situation like this, it states that we want to know the limit of the function, f of x, is this graph, as x approaches 1. So x is going toward 1, and the function is actually itself going to 1. So I'm going to say its limit is 1. That's where it wants to be. That's where it wants to go. If I approach it from this side or from this side, the function still wants to be 1. It's just that it can't be. It's defined as something else. Later on, there are problems in the book that talk about machines that can't be defined for certain values. The U ratio isn't right for operating it like that. So it's given another defined value if the situation occurs. This is where it would like to go. Let's take another one. Limit of our function f of x is approaching 2. Well, when they say x approaching 2, it necessarily means from both sides, as it gets larger or as it gets smaller. If we look at our function f of x, it's defined to be 2, the y value, but if we approach it from the right or larger values, we see our function would really like to be 3. So there's this big gap in what it's defined as, what it wants to be. Not like over here, where it was clearly what it wanted to be from both sides. So we always note that if the function is different from the left and different from the right, it's like telling a friend to meet you on 2 different streets. You can't be up here and down there at the same time. So we say this limit does not exist. DME does not exist. If it's different from one side than the other, your friend's going to be lost. All right, the function as x approaches 4. So clearly from either side, the function would like to be 2. And there's a pothole there, but you know where you want to go. No problems approaching it or seeing that pothole from either side. In this problem, we're asked to find the limit of a rather large polynomial, enumerator polynomial divider, which makes a rational function. And we're supposed to find this limit as x gets very, very large, infinitely large. So one algebraic maneuver that works quite nicely is to look for the largest power that exists in both the numerator and denominator and use that as a divisor on each term. So we observe that x to the 4th is the highest, and we divide each term by x to the 4th. Well, you can see that what's left on the first term in the numerator is 2. And what's left, I should probably write that instead of spoiling the answer for you. So what's left here is 2, because the x4s are going to cancel. And we see this one was 9x cubed divided by x to the 4th. Well, as x gets really, really large, the denominator is going to overshadow the numerator. So a small number divided by a large, much larger number, and the denominator is getting pretty close to 0. More so here because it's going to be 2 divided by x squared, x getting size of the national debt. It's going to be pretty much 0. 6x to the 4th divided by x to the 4th leaves us a 6 again. And again, same scenario plays out here, that these numbers are diminished by the ever-increasing denominator, because this is going to be 3 divided by x, x getting larger and larger. 7 divided by x squared doesn't have a prayer, it's going to be 0. So this leaves us with 2 over 6, or 1/3. If you check this out on your calculator and went way out on the x-axis, you would see that that's where the functional value is heading. It's coasting toward a horizontal asymptote of 1/3. Not so hard. two more limit problems. I think I forgot this one from the previous page. Let's work on this one. And we see that x wants to approach 4, which of course would be a no-no, because if we put a 4 in here, we'd end up with a 0 in the denominator. Can't work with that. So let's look at this as the limit as x approaches 4 of its factored form. The numerator is a difference of squares, which factors nicely into x plus 4 times x minus 4. And one of those factors can slash reduce with the denominator. And then it's safe to put the 4 in to let the x slide all the way to 4, no prohibitions anymore. And it's the same value, just reduced. We pulled out a factor of 1. X minus 4 over x minus 4 is 1. And the limit then of x plus 4 as x approaches 4 is 8. And this one, I just did on the calculator. Again, it's unsafe to put a 0 in there, turn the denominator to 0. If you try it in your calculator, it won't do anything. It'll try to have an error. And so you can pick tiny values, like let x equal 0.001, let x equal 0.0001, let x equal point, you got the picture? And it looks like it's settling, about 3.3. And just be careful with your parentheses and your exponents so that you've got the right format. And we could graph the function and see if, evaluate it then at these values and see where it's going. Don't put in 0. Thank you. In this problem, it says plot the tangent line to the graph at x equals 2. So at x equals 2, I did my best to use a ruler and just touch it down once, just kiss the graph when x equals 2, trying to make a straight tangent line that doesn't cut through the function, but just merely touches down upon it. And my goal is to measure the slope of this line, because slopes are rate of change, just like derivatives, and tangent lines are rate of change. You think a tangent line is a picture of a slope or a picture of a derivative. And I just grabbed some easy blocks on my graph paper, and I found a run of 1 and a rise, which is a drop of -1. So when I put those in my understanding of slope, change in y over change in x, I have -1 over 1, or my slope is -1, which makes sense. It's a gentle slope and it's descending. -1 looks pretty believable. And so quite often this is very useful because we don't have any more data. We just have a picture of a function that's happening at a certain point. And we can use that to try to forecast what's happening next. For example, if the line in the function didn't continue here, we might believe that it's going to follow the tangent line instead, because that's the behavior we know. And what do they say? Future behavior is best predicted by past behavior. So if it's been tooling along like that, it might just likely keep that up. In these problems, we don't have to use limit definition of derivative. We're allowed to use power rule. So we know that the power rule says given f of x equal x to the n, its derivative is equal to n times x to the n minus 1. And if there's a constant multiplier there, such as f of x, if f of x equals ax to the n, that constant multiplier would also be in the derivative. We would just multiply n times the a, but still reduce the power by one integer. So let's practice on the first one. The derivative is equal to, and don't write equal here without writing derivative. This is the function, this is derivative we're about to take. So it's going to bring the 7 down, x 7 minus 1 is going to be 6. And isn't math beautiful? Comes out so nice. Here's a case where we're going to acknowledge a constant multiplier. So our derivative q prime, or the derivative of q evaluated w, is going to be 11 times 2, 22, w, 11 minus 1, 10. And on this one, before you do anything, rewrite the function as x to the 1/2. It's a lot easier to work with. Then our derivative is 1/2 x to the minus 1/2. You have to practice your fractions. You have to practice your negative numbers. Rewrite this as q to the minus 1. As is, we got to use quotient rule. We don't have quotient rule yet, so let's use power rule by writing it as a power in the numerator. So our derivative of the p function is equal to, just like before, negatives and fractions don't stop us, minus q, and 1 less than minus 1 is minus 2. So by doing several limit definition of the derivative problems, you're entitled to use the power rule.